I usually
Then
break.
he breaks
I
it.
usually break it before I fix it.
Then you get to learn both how to fix it and break it.
There you go.
Professor, I have a question on the homework.
Yes.
Some of them say A, B, C, D, E,
Yeah.
and some of them don't have letters on it. What does that mean? Like, for example, chapter 1 says 2, A, B, C, D,
Yeah.
E, and then it says question 3, 4.
Yeah, that
without
means
letters
do
on it.
them all. If I don't say what letters.
Okay.
Yeah. That's not what you wanted to do. That's what I meant.
Holy crap, like you're early.
Oh, that's why. You put A, B, D, E, not C.
Right.
That's
Yeah,
why.
because I wanted to. Yeah.
And I didn't notice that part.
I didn't like C.
What is that? That is an empty one. No. Is there any yet?
Yeah, there we go. I think I already sent it over. Yeah, I already did that one.
This is, you can't anything like this? Put it out there?
Music's so much nicer than mine.
Actually?
How'd you make it look so good?
I'm very used to doing diagrams on Google Docs, but this is horrible.
I did mine on paper, so.
I can
Oh,
only
so
read.
you just send pictures.
Hmm?
You just send pictures of your work.
I can't it just,
You go like screenshot each one.
I can't send this as a PDF and,
Yeah, you have to send it for each individual question.
you can just screenshot it, isn't it?
Yeah, so you do like screenshot all. Those look beautiful though.
Maybe they took some time, but it's worth that time, because you can always re-edit it.
Anyone got homework questions?
For exercise 2, you say list all strings of length 3. So we just stop at 3 when we're at 3.
Yeah, yeah, right. Mm-hmm. Can I look at that again?
Sure, I really like it.
I think so. I'm still like a big listen to my
Yeah.
Tuesday morning. So here, I'll start just feeling extra adventurous today. It's more like life-threatening.
I feel like I barely saw you yesterday.
Seriously, where were you?
I was in a lounge, and then I played basketball for like 2 hours.
I was
Maybe
in
that's
too,
why.
but I didn't see your handsome face.
And
So for physics, there's no lesson. And all you do is you just it's blackboard.
Yeah, pretty much. You just the portal blackboard.
No, I didn't realize that's how it goes. So it's so confusing.
Yeah, it's
So
really
it's
fun.
so it's good after the answer, so you can always go right.
Yeah.
is there a blackboard for something
I
else?
couldn't figure out one if I'm an editor.
No, I never used the blackboard.
Oh, just your website.
Yeah.
Yeah, the units were.
I actually like that.
Yeah.
Yeah.
Everything's on that one page.
Right, yeah.
And then,
I don't like how Blackboard is like
right, like the actual answers what did.
locked down, like you need a password to get in.
Oh.
Yeah, I'd rather just have everything.
I feel like the best solution to get things right in the class is worst case you just take it out.
And you don't have to worry about re-logging in.
Yeah,
to Blackboard that shuts
Sometimes
that keeps you every like
Yeah,
3
right.
You're like moving parts.
I find it easy, I mean, I just write the HTML by hand.
Actually, number 3
Oh.
Actually creating stuff in Blackboard, like you gotta click all these things.
solution. I thought it reading right, but I still got.
It'd probably be easy if I learned how to do it,
I still don't know. I think I still don't know.
but. Anybody got questions on the homework? Yes?
Can you watch it? Didn't watch it?
That's my only, I'm thinking about that. There's no way spend money.
Budget.
This one's about $12.
I was gonna say get a Casio. The premium, the all sustainable.
600.
Yeah, with the top solar and
Yeah.
would you get the actual Casio or the computer shape or the square one?
Oh, the actual one.
Yeah.
Yeah.
I'm just too skinny, but
I don't even think I can roll it.
I would have gotten $100.
No, it's just the actual dial itself is.
It's huge.
Yeah.
Usually Casio or like the big rugged. Like, this is the smallest watch I've ever found. It's still kind of loose.
Yeah, that's fine.
What's the
A700.
A7? Yeah, it's the A7. Whatever.
Not the premium version, but it's a basic.
Hey man, I still gotta buy one.
These
The
are
next one,
different.
costs like $60.
And
This one was like 27.
And also K.
Oh, yeah, yeah. I mean, 27 is
and-
fine,
and-
it's 16.
No, it 27 is really
Hey,
expensive.
Numbers, let
I'll
me
show you
see.
what I'm looking
We'll hook you up next time.
Zero or more.
Did you start the task picture? This
Does that just mean like VA to like the N or
Is
something?
that a diaper tag?
Yes, it's 300 versus doubles.
All right, I think it's time to get started. As you may know, the first homework assignment has been posted. It's going to be due tomorrow evening on Gradescope. Please let me know if you have issues using the Gradescope. I hope that you have done that before. You should be able to just write all your answers on paper and then take pictures of them, or you can write them electronically and you can submit a PDF or just submit like individual screenshots or something if you want to. Check it out. Let me know if you have technical difficulties, or if you have like actual questions about the homework. I would be happy to discuss also. All right. So we are going to talk today about. We sort of left hanging an example from last time was a DFA for binary numbers, and I wanted to accept if the number is divisible by 3 and reject otherwise. All right, so if you recall, we can write numbers in binary. I'll just make a short list again. Looks like this, right? Oops. So this would be 0 and 1. This is 2, this is 3, this is 4, this is 5, and so on. 6 would look like the next number I have to carry. All right, it's just like ordinary decimal numbers, but you gotta carry almost every time. You can only use the digits 0 and 1, and so there's a lot of carrying going on. Can you all see the screen all right? I think I have I can't see it at all from here, but that's just because of my angle, I think. I hope that you can all see it. There's one back there which doesn't seem to be working. They monkeyed around with the wires over the weekend. All right, so our DFA is going to accept the string if the number is divisible by 3 and reject otherwise. What's interesting about this is the DFA, as always, has to read the string from left to right, which is kind of backwards when it comes to ordinary like reading of numbers. We sort of treat numbers from right to left. This is actually a vestige of the fact that we use an Arabic number system, and the Arabic alphabet is written right to left. Which is why the numbers, in some sense, we write numbers sort of backwards from English conventions. Anyway, how are we going to do this? I suggested at the end last time that the proper way to think about this is really in a machine of 3 states. And there are, because when it comes to being divisible by 3, there are really sort of 3 options. It could be that your number, I'm going to write it this way, x is 0 mod 3. That means that your number really is divisible by 3. But if it's not divisible by 3, it might have a remainder of 1 when dividing by 3. Like it might be 1 more than a multiple of 3, or it might be 2 more than a multiple of 3. So I'm going to write that as this, and also this. These are my 3 different states that a number could possibly be when it comes to trying to divide a number by 3. It is either actually divisible by 3, or it's 1 extra, or it's 2 extra. All right. I would like to think about these binary numbers. I mean, the whole game here is deciding where the arrows go, right? And I suppose it's not even obvious that this is going to work at all, but it is. How we decide where the arrows go, it has a lot to do with, we have to actually think more fundamentally about how a binary number behaves when you read it from left to right, all right? For example, if I have, if I see a number x, and then we read another digit on the right-hand side. So if we see a number x, binary number, then followed by a 0. So what I'm talking about is something like, if I see 111, which is the number, I didn't write it, that's 7 in binary, versus 1110. This number is actually 14 in binary. I just did that in my head because actually I know some kind of sweet trick for binary numbers. Anybody see what's going on there? When you add a 0 as the rightmost digit in a binary number, can you predict what effect that has on the value? Yeah.
Double it?
It doubles it, yeah. Can you say why?
No.
No, it's a little early in the morning, perhaps. Anybody have an idea about this? It's true. It doubles the number. You should think of this analogously in a base 10 number system. If you start with a number and then add a 0 on the end of it, on the right end, you have multiplied that number by 10, right? It's because of the way the base works. Really, when I see a binary number 111, this means, in binary, it means 1 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0. Like this binary number, this is the 1's digit, this is the 2's digit, and this is the 4's digit in binary. All right. And if I add an extra digit to the right here, what the effect is it just basically shifts everything over to the left by 1 digit, which has the effect of increasing all these exponents by 1, which is to say it multiplies everything by 2. Just like in base 10, when you shift to the left, it multiplies everything by 10. In base 2 or base whatever, shifting digits to the left multiplies everything by the base. All right, so if we see an x then followed by a 0, so maybe I'll just write this down here. Adding a 0 to the right of, in binary of course is what I'm talking about, x, changes it to 2x, right? If you had some number, x, if its value was x, and then you add a new digit on the right side, it's a 0, the effect is it becomes the number with value 2x. All right? Okay, what about adding a 1? There's only, I mean, we have to, I'm trying to think in a systematic way about sort of what happens as you're reading a number in binary from left to right. Now, if you add a 0 on the right side, then that doubles the value. What if I add a 1 on the right side? Can anybody say, I want to write a sentence sort of similar in structure to this, adding a 1 to the right. Adding a 1 to the right of binary x changes it to, can anybody say? Yeah?
2x plus 1.
2x plus 1, yeah. Adding a 1 is just like, it's 1 more than if you had added a 0, right? And so the value, if you add a 1 on the right side, becomes 2x plus 1, all right? And this is actually how we can predict where the arrows go in our diagram there. So for example, if I have if x is already 0 mod 3, what about, x followed by 0, all right? Because this is what we have to decide in our diagram. If you have a number which you believe is already divisible by 3, and then you stick a new 0 on the end of it, is it still divisible by 3, or does its remainder become a 1, or does its remainder become a 2? This is what we got to think about. If x equals 0 mod 3, then what about x followed by 0? Well, we can make a simple little argument here. What this means is that x equals 3k, right? For k being some integer. This, I hope you remember what your mods mean. X equals 0 mod 3 means x equals 3k. So it becomes, when I write a 0 after it, it becomes 2 times 3k, right? That number followed by a 0, it multiplies it by 2. And so it used to be 3k, now it's 2 times 3k, also known as 6k, I suppose. Can you say, is this number now, is it divisible by 3? Is it 1 more, or is it 2 more? I think it is still divisible by 3, right? This is, if you like, by some rule about something or other, this is still divisible by 3, all right? So, my conclusion, all of this has led me to believe so far, if the number is divisible by 3 and then you see a 0, it is still divisible by 3. So, in the diagram, if you still have the diagram here, I'm going to do one of these, all right? If the number is divisible by 3 and then you see a 0, it's still going to be divisible by 3. Where do all the other arrows go? Well, we should be able to just figure them all out in the same way that we just did. This is, you have to go through basically 6 different little bits of reasoning in the same way as this right here. All right. So I hope this is making sense to everybody. How about, again, from this state, if we begin with x equals 0 mod 3, what about x followed by a 1? So if x equals 0 mod 3 and we read a 1, that is to say x equals 3k, of course, then it becomes, remember when you read a 1, the effect is to multiply by 2 and add 1. So it looks like this, 2 times 3k plus 1, like that. Reading a 1 multiplies the value by 2 and then adds 1. Okay, and is this number, is it a multiple of 3? Is it 1 more or is it 2 more? Show me the fingers. Yes, they're all showing me the one finger. Not that one finger, the good one. All right? Yes, this is 1 more than a multiple of 3. If you like, if you want to be convinced, again, you can write it like this. It's 3 times 2k plus 1. So it is a multiple of 3 plus 1. So this is, so on the diagram, what does that mean? It means if I'm in this original state here and I see a 1, I should go over to this state. All right? Like so. Because if it was divisible by 3 and then you see a 1 next, now that number is 1 more than a multiple of 3. All right? Okay, I mean, this should work, right? If we just work this out. So from here, I need to think about from here. What if I read a 0? What if I read a 1? And then also from here. Let's try it out. So I'm just going to say the same stuff basically, but this time I'm going to say if x equals 1 mod 3, of course this means x equals 3k plus 1. That is 1 more than a multiple of 3. And we read a 0. It becomes 2. It gets multiplied by 2, right? Now make sure you put your parentheses in the right place. It's this. 2 times 3k plus 1, right? Whatever it used to be is now multiplied by 2. What is that? Is it 1 more than a multiple of 3 or 2 more or 0 more? I believe it is 2 more. I see the fingers again. Yeah, if you distribute the 2 here, it now says 6k plus 2, which of course is 3 times 2k plus 2. I'm just trying to write it explicitly as a multiple of 3 plus 2 extra, all right? And so that means if you're in the 1 state and you read a 0, you go over to the 2 state. I hope you don't mind me scrolling. It's like that, all right? If you're 1 mod 3 and then you read a 0, you should go over to 2 mod 3. All right, and the other possibility for this one, so if x equals 1 mod 3 and we read a 1, then x equals 3k plus 1 becomes, this one, when you read a 1, you multiply by 2 and then add 1. So it's going to be 2, 3k plus 1 plus 1, right? You could also think it's just 1 more than the previous one. Anyway, this, if I distribute out, it's 6k plus 2 plus 1, which is 6k plus 3. And what is that, mod 3? It is 0. Yeah, this actually is a multiple of 3. You could factor the 3 all the way out here. It's 3 times 2k plus 1. So this is a multiple of 3. And so this one is 0 mod 3. That means if I'm in the 1 state and I see a 1, it goes back to 0, like so. All right, just 2 more. I have to consider this state here, x equals 2 mod. I just wrote mod. I meant to write mod 3. X equals 2 mod 3. All right, same business. I mean, once you know what you're doing here, these are not really hard. You do have to think through all of them, but not a big deal. And we read 0. Okay, so we begin this time with x equals 3k plus 2. And this becomes, reading a 0 multiplies everything by 2. So it becomes 2 times 3k plus 2. And what is that in terms of mod 3? If I distribute the 2, it looks like 6k plus 4. This is 6k plus 3 plus an extra 1. This is 1 mod 3 because I pulled apart the 3 there so that the thing in the parentheses is a multiple of 3 and then it's 1 extra. So if I'm on the 2 state and I read a 0, I go back to the 1 like so. All right, there's a pleasing little symmetry in the arrows there, which, you know, if you don't think of it this way, you have no reason to expect that kind of symmetry in the diagram. But there is. Okay, one more. If I'm in the 2 state, mod 3, and I see a 1. Come on. So if x equals 2 mod 3, pencil, and I read a 1, then I see x equals 3k plus 2, and this becomes 2 times 3k plus 2 plus 1, right? We multiply by 2 and then add 1. And this, when I multiply it out, that's 6k plus 4 plus 1. That's 6k plus 5, which is the same as 6k plus 3 plus 2. That's 2 more than a multiple of 3. So if I'm in the 2 state and I read a 1, it goes back to the 2 state. And this is our DFA. Very simple, actually. 3 states with those arrows. We should write, you know, every DFA has to have a starting state and the accepting state. So this one, the 0 mod 3 is meant to be the accepting state because I said it should accept all numbers which are divisible by 3. And what should the starting state be? You have to think about sort of, before I read anything, which would represent like the number 0, where should I start? Yeah.
Upper left.
Yeah, this one here. That's because the number 0 counts as being divisible by 3. So you should start in that state. All right. And that's about all there is to it. This one really works. If, you know, I asked you last time, for instance, I just made up some big binary number just for fun. Can we decide, is this thing divisible by 3 or not? How we do it? I mean, not knowing about this DFA, it would probably take me a while to figure that out by hand. If I had to do it by hand, I would probably just convert this to base 10 and then use some kind of tricks for divisibility by 3 and base 10. But on the diagram, it's quite easy. I'm going to try to follow along here. It'd be best if I could use 2 fingers. I only have one red dot though. So I go 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0. Apparently this is one more than a multiple of 3. All right? Pretty awesome. You can impress your friends. Ask them to tell you a binary number, digit by digit. Actually, if somebody just reads the number out to you, you can follow along as they're saying the digits and tell them the answer immediately when they get to the end. All right? That's a little party trick. You could memorize this diagram and do it in your head if you want to. It'll be the last party you're ever invited to. All right? So anyway, this was an example of a DFA which can actually perform a allegedly like useful or complicated computation. All right, I don't know how useful this is really, but it is mathematically sophisticated. It's something that without thinking about it in this way, I wouldn't be able to do this in my head. Although I suppose I could do it in my head if I memorized the diagram. All right. Can I just say, it's not hard to make similar DFAs that test for divisibility by 4 or 5 or whatever for binary numbers. It's just the same basic idea. All right. That's the last of our sort of example DFAs that we're going to talk about. There's plenty on the homework for you to practice with. I hope everybody's feeling good about DFAs. I want to talk a little bit abstractly today for the next little bit at least about what is a DFA? I mean, really. Now, as I've described it so far, I don't know if you feel like I have been, but actually I have been slightly informal when it comes to telling you what is a DFA. I've said sort of a DFA is like this, meaning it's got some states which are like circles, and it's got some arrows. But I don't know if you remember the first day of class when I was talking an overview of the history of the subject. You will recall the whole subject of the theory of computation, or the concept of talking about algorithms at all, was motivated because mathematicians didn't actually know what the proper definition of an algorithm is in terms of set theory. And Turing's big idea was an algorithm should be defined in terms of set theory as any kind of thing which can be computed by a machine. And then he described his machine in terms of set theory. So the whole purpose of doing all of this stuff in some super abstract level is to do it in the language of set theory. And this here I have not described really in a coherent way in the language of set theory. All I said is like a DFA is something that kind of looks like that, which is not really a real mathematical definition. All right, so what is a DFA? I want to talk about a formal description using sets, all right? This is sort of what's necessary if you ever, for example, wanted to write a proof about DFAs, about, like I said earlier, it turns out that there's no DFA that will tell you if a string has prime number length or not. Now, if you actually wanted to prove that, it would require having a real understanding of what exactly counts as a DFA and what doesn't, all right? And the things that I've said so far are not really adequate for writing that kinds of proofs. So we need a formal description using sets. The diagram is an informal view of what the DFA is, but the true nature of the DFA is not the picture. It is just a thing, an abstract thing in terms of sets. So I'm going to say, just before we get to the formalism, the important ingredients. As far as I can tell, there are 5 important ingredients that make up the DFA diagram. First of all, there are the states. You know, the DFA that we just wrote had 3 states. So that you could think of as a set, right? There's a set of states, all right? So that feels like a set to me. That's a set of states, and there has to be finally many of them. There's also the arrows, the transitions. On the diagram, we draw them as arrows, but we call them the transitions. Those are the arrows. And you could think of them as another set. There's a set of arrows. You could think of them in that way. Although, it's actually more mathematically convenient to think of them as a function, right? It is a function which says, if I start in this state over here, then what state do I end up with over here? So the transitions are going to be described mathematically by a function. What else is important? Those are the main major ingredients. What else is important in a DFA? There's, you can just think about the diagram. There's like the circles, the arrows. What else? Yeah.
The accepting and rejection state.
Yeah, right. So the accepting states. I don't know if I've ever mentioned this, but you are allowed to use more than one accepting state in a DFA. It doesn't have to be just one. The accepting states and the rejecting states. So actually in the formalism, we just say what the accepting states are, and then everything else is automatically, by default, a rejecting state. So the accepting states, this is also a set, right? In fact, it is a subset of the first set up there. But anyway, this is going to be a set. What else? Yeah.
Like the starting.
The starting state, right? This is not a set, this is a particular state, but it's really an element of the first set, right? If the first set is the set of states, this is an element. And then finally, the last of the ingredients is something that you don't even really think about on the picture, but it is underlying everything that goes into the picture, and that is the alphabet. And this also is a set, all right? And if you know all of those things, then that is a complete batch of information which suffices to define the DFA. And so that's really what our definition of the DFA is going to be. The true nature of the DFA is not the picture. The picture is a representation of the DFA, which is easy to look at. But the true nature of a DFA is just this stuff, all sort of bundled together. All right, so my definition, the actual definition of a DFA is a 5-tuple. That means, tuple is like an ordered pair or something is two things, or an ordered triple. A 5-tuple is just a single thing with 5 parts to it in a particular order. And I'm going to write it like this. M for machine is a tuple. Q, sigma, delta, Q0, and F. We are basically always going to use these notations for the 5 parts of a DFA. And I have to tell you what each part means. So where Q is a finite set, this is the set of states. All right, sigma is another finite set. This is the alphabet. I'm putting the word, alphabet in parentheses because I'm trying to define what a DFA is. The fact is, the Q can be any set. The sigma can also be any set. Our interpretation of this is that the Q represents the set of states, and the sigma represents the set of alphabet symbols. All right, then delta. The delta is complicated. It is a function, though, and it is called the transition function. And if you think about a standard DFA picture, I'm going to scroll away for a moment just to look at this picture again. All right. What we have for these arrows, every arrow has an origin state and also a label on it. Like if you're looking at this one here on top, its original state is that one, and then it has this one on it, and then it has some state which is the answer. But I also, from this state, I could do the 0, which comes back to here. So my function is really going to take, as its input, it takes a state and also a letter. And it says, where do you end up if you start in that state and read that letter? where does it go to? So the structure of this kind of function is, this will look a little complicated. I'm going to try to write the domain and codomain of this function. Delta, I'll write it and then I'll say what it means. All right? Q cross sigma to Q. All right? What that means is, so this is a function, and it's called the transition function. I hope you remember from your discrete math class, Q cross sigma means the set of all pairs, where the first thing is from Q and the second thing is from sigma. So this means this is a function which its domain is a pair. What you plug into this function is a pair, some state, comma, some letter. And then what comes out is the answer is another state. So this says if you start in some state and you see some letter, what state do you end up in? That's how the delta works. We're going to talk more about the delta in a moment. Last two ingredients are much simpler. Q0, Q0. This is simply an element of Q. This is the starting state. Remember, Q is the set of all states. The starting state is just chosen to be one of those states from the set of Q. And then F is the set of accepting states, and it can be any subset of Q, which we write like that. This is the set of accepting states. All right. Q is the set of states. And so Q0 is just one of those states which is chosen. And then F is some subset of those states, which are called the accepting states. All right. This is the true definition of a DFA. I don't know if anyone is wondering at this point. Oh, if this is the real definition, why didn't I just say this in the first place? It's because this doesn't look like anything. If you just say this, it's just a set, another set, some function with the weird domain, then an element, then a subset. That's what a DFA is. Although, unless you have the interpretation of all of this as a diagram, it really doesn't mean much of anything. But when you want to write the real mathematical definition of a DFA, that's what it's got to be. All right. Let's write an example. So a typical, this is actually very easy to work with typically. A typical homework assignment about this would be something like, if I show you a diagram, then can you write the actual true definition of that DFA in terms of the sets? So here is a typical example like this. How about, here is a DFA diagram. I'm going to give names to all the states just because they will be easier to discuss if I do. Little pro tip, draw the name of the state first and then circle it. It's much easier than writing inside of a circle. Okay, so there's an arrow there with a B, there's an arrow here with a B, there's an arrow here with the A, and then a comma. All right, this is a DFA. Your job is to write this DFA formally as a 5-tuple. All right? So you have to write down what each of the 5 parts are. And this is most convenient to say it's M equals, all right? And I have to just write down what are all of the 5 parts. So what is, the first part is big Q, that is the set of states. What is the set of states? Well, there's 3 of them here, S1, S2, S3. And I just write them, S1, S2, S3. All right, that's the first thing in the tuple is the set of states. The next thing, you have to write them in the proper order. The next thing was sigma, the alphabet. What is the alphabet here? It's also a set. What do you think?
A and B.
A and B, yeah, excellent. Right, that's the alphabet. Okay, next is the transition function. Now, to write the transition function is the most complicated part of this, so I'm going to just temporarily put a delta there, and then down here I'm going to say where delta equals blah, 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 blah. But can we fill out the rest of it? The delta is the most complicated part to describe. Next comes Q0, right? That is the starting state. What is Q0 in this example? Yes?
S1.
S1, right. Just like that. Should I put it inside the curly brackets? The answer is no. Almost fell down. It should not go in the curly brackets because this is meant to be an element of this set. So it's just an element of that set, not another set. All right, and then finally, the set of accepting states. Here should have the brackets because it's a set, and it is the set of accepting states, which in this case are S1 and S2, like so. All right? You basically just looking at the diagram and pulling out what are the essential ingredients. All right, and then at the bottom we have to describe what delta is. And this is the most complicated part. Probably I shouldn't have written an equal sign there because you can't even really say it specifically in one line here. What is delta? It's a function which takes pairs and give you answers, but there's not like a formula for delta. The only way to describe delta typically will be just writing down what all the values are. So delta, of course, goes Q cross sigma to Q, all right? So the domain of delta looks like a pair where the first thing is a state and the second thing is a letter. So a typical evaluation of delta looks like this. Delta of, let's say, S1 and A equals, what the meaning of this is, if you start in this state and then you see A, then where does the arrow go? And if you look at the diagram, the arrow goes back to state 1. So this is like that, all right? And what I've done here is basically that describes this arrow right here. Now that's not, I haven't described the entire function, that's just one of the values of the function. If I want to describe the entire function, I just have to write down what all the other values are. So this is a bit of a pain, but it's not so bad. I'm also going to list out what is delta of S1 and B. I'm going to list out all the possibilities. That's really the only way to go about this. I also have to list delta of S2 and A, delta of S2 and B, and finally delta of S3 and A, and delta of S3 and B, all right? When you have a function, an abstract function defined on abstract sets, this is not like, f of x equals sine of x. There's no like traditional algebra formula for what this function is. It's just some function that is related to the arrows, and you just have to say what all the answers are. And they're not hard, you know what you're looking for. What is delta of S1 and B? That means if I'm in state S1 and I see B, where does it go? It goes to S2, so this is S2. Delta of S2 and A. Could I ask the audience about this? Maybe I will, could I just like point at people going around the room? Are you prepared for this? It's now 10:06. You've been here for 36 minutes, right? Yeah, not long enough. Can I start in the back corner? Can you say your name and then tell me what delta of S2 and A is? Maria and S3. I agree. S2 with an A goes to S3. Great. I will probably immediately forget your names. I apologize. Next.
Luke, it'd be S2 for S2.
Luke says S2. Yeah. S2 and B goes back to S2. Great.
State 3 of A is equal to state 3.
Yes. And your name is?
Joe.
Joe? All right. Thank you, Joe. And finally.
Melissa, state 3 and B goes to state 3.
Yes, back to state 3. Excellent. All right, thanks. That's it. This now is the complete description of this DFA formally. All right, and there really is no better way to write out the delta. It's just like that. Any thoughts about this? This is not hard. I don't often like go around point at people and ask questions, but this I figured is easy enough. All right. Excellent. One more thing that I want to talk about is what does it mean for a string to be accepted on a DFA? This is also something we should describe formally. If I ask you just informally, what does it mean for a string to be accepted? Like if I say A, B, B, B is accepted, I mean, informally I would say, well, if my red dot starts here and then I jump around and go A, B, 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 then it's still accepted. This is not a very mathematically meaningful way of saying things, though. Really, when it comes to accepting a string, it has to do with sort of plugging into this function over and over again. If you start in the accepting string, really what it means is, for instance, if I do A, B, 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 it means if I start here and I plug in A to this function, and then B, and then B, and then B, where it ends up is in one of the accepting states. That's what it means for a string to be accepted. Let's talk first about plugging things into the delta over and over again. So we want to, really what we want to do is plug entire strings into the delta, right? Which, I mean, the delta, this function delta, as written, you are not allowed to plug a string into it. You have to plug a state followed by a single letter. But we can invent something which is basically like the delta, but you're allowed to plug a whole string into it. This is called, so delta is called the transition function. This, what I'm about to say, is called the extended transition function. It is a function which you are allowed to plug a whole string into, and we write it as delta star. That's because the domain now is no longer q cross sigma. If I say the domain is q cross sigma, that means you have to plug a single letter, because that's what sigma means. Instead, I'm going to write q cross sigma star to q. Remember, sigma star means the set of all strings using the alphabet sigma. So the extended transition function is one where you don't just plug a single letter in, you can plug a whole string in. But it still means the same thing. It means if I start in a string, or if I start at some particular state and I plug some string x, the answer should be, sort of informally speaking, where you end up if you start in state S and read the string. Sorry, I ran out of room over here. X, right? That's the meaning of, sorry, I meant delta star. When I write delta star of a state followed by a string, it means you read that whole string making like several jumps around in the diagram. And then the answer is just wherever you end up at the end of that. All right, this is called the extended transition function, delta star. So for example, in our DFA diagram up here, I'm just going to copy it down here, if I may, duplicate. So this guy here, if I do something like delta star of S2 and BA, AB, what is that? That means if I start in S2 and I read this whole string, where does it end up? So starting here, I go B, A, B. It's S3. Right? So that's the meaning of the delta star. All right. Delta star has some important properties. Two of them are obvious and one is a little confusing. Let's just talk about properties of delta star. I said two of them are obvious and one is kind of interesting. What if I do delta star of some state? Often our states we're going to call little q because the set of all the states is called big Q. So Q is a state. And then what if we start in a state and read the empty string? What should that equal? Actually, I didn't really say that up here. I said it's where you end up with if you start in some state and then read the whole string. I think there's only one sensible thing to say about this. But if I start in state Q and I read the empty string, where do I end up?
Where you started.
Yeah, where you started, which would be Q, right? This is like if you start in state Q and you don't do anything, you end up in state Q. So this should be Q. It really doesn't make any sense to say anything else. Although this has to be defined. You don't want to say just like this is nothing, because empty string is a legal string, so you should be able to plug it into the delta star. All right. Okay, that was one property. Here's another interesting but simple property. What about, this is about if the string, if x happens to have length 1, that is to say, i.e., x is just a single letter, then delta star of q and x, if you just read a single letter, this is actually, it's just the same as the ordinary delta. Not with the star, right? This is another obvious property of the delta star. If the thing, the delta without the star is meant for just individual letters. And certainly, if you are using an individual letter as if it were a string, you're going to get the same answer if you use the delta star. All right? And then, I said that there were 3 properties. 2 were simple. Those are the 2 simple ones. Here's the more complicated one. It is about this. There's a rule for this. I'm just going to write the first part first. Delta star of q and xy. I would like to be able to kind of simplify this. And I think the idea behind this is simple. It's just, if I start at q and I read x followed by y, the idea is you do the x first, and then wherever you end up there, you do the y from there, all right? So I want to write, I'm about to write, don't copy this down because this is not right, but it's basically this followed by this, right? You read the x first, and then wherever you end up, you read the y from there, okay? But actually, this is not correct the way that I wrote it. There's a few things wrong with this. One is, I say you read the x first, and then you read the y from there, but I put another q here. That q actually is not right. It shouldn't be, you don't read the y from q, which is where you started at the beginning. You read the y from wherever you ended up after the first. And then the other thing that's wrong with this is, actually, it doesn't make any sense to write these 2 things next to each other. The answer of a delta star is a state, and the answer of this other delta star is another state. You can't just write 2 states next to each other. That doesn't mean anything. So can we think about how do you actually say what I'm trying to say here? What I'm trying to say here is you start in Q, you read X first, and then wherever you end up, starting from there, you read Y. That's something like that. Anybody got any ideas about this? Yeah?
You could do like delta star of qx equals like q2, and then like delta star of q2 comma y.
Mm-hmm. I like this. Yeah. Actually, so she said you. We're gonna write this in a slightly simpler way. She said like this, something like let Q2 be that, and then you're gonna plug that inside of the next delta, right? Actually, this I'm not gonna write this intermediate step, but really what you do is you plug this inside another delta star, all right? So rather than what I wrote before was I wrote one next to each other. That doesn't mean anything. Really what I meant was one of those should really go inside of the other one, all right? So it's gonna look something like delta star of Q and X, right? This is confusing. What this one on the inside means, this is the state you end up with after you start in Q and you do X. And then, starting from there, you read Y. It's that, all right? I think this is what you said. Without, you don't actually need this business, right? This is very weird looking if you look at it out of nowhere, but this is what it means. It says, if I start at Q and I read X, Y, this is the same as, first of all, start at Q and read X, and then from there, you read Y, all right? This is a weird-looking formula. That is the third interesting property of the delta star. Anyway, these properties we're going to use, although we're not going to get to use them today. Can I just say, though, in our remaining 3 minutes, we can say the true definition of what it means to be accepted by a DFA. So here's the definition. For a DFA M, which is Q. I'm not going to draw any diagrams or anything because the diagram is just a representation of the DFA. What the DFA really is just that tuple. For a DFA, m equals that. Then we say a string x in sigma star is accepted by m when what I want to say is if you start in the starting state and you do x, it ends in an accepting state. Can anybody think of how would I write that in using all of these formal symbols? Actually, you can write that in a specific equation. If you start in the starting state and you read x, then you end up in an accepting state. That's what I want to say. Got an idea?
Yeah, could you say sigma star of qx is equal to the f,
Yeah, I like this. This is almost perfect.
or like some little f in f?
Yeah, right. So delta star of qx, that means if I start in state q and read x, what I end up with is one of the accepting states. Now, you can't say equal here because f is a set and this is an element. You can say this equals some little f where f is an element of big F, or it's actually easier to just say that, right? Delta star of q and x is an element of the set of accepting states. Actually, there's one little thing that's not quite right about this. Anybody feel? What you need to say is, yeah?
Oh, it's only x instead of a string?
No, this x here is okay. This x is some string.
Oh, yeah.
So you can put x here. The point is, something is accepted means if you start in the starting state and you read at the string x, then it ends in one of the accepting states. I didn't actually say anything about the starting state here. Really, this q needs to be this, specifically q0, the starting state. So this q is q0. If I start in the starting state, I just put a little q naught right here. If I start in the starting state and I read x, the result is an element of the set F. Can I just write this? Sorry, I know it's time to go. The way we write this is, the language is the set of all accepted strings. It's this, x in sigma star, such that delta star q0x is an element of F. All right? This is super formalized, right? But this is what the language of the DFA means. It is all strings in the alphabet sigma, such that this is true. All right, we will do some more business with this next time. Please let me know if you have homework questions. See you tomorrow.
You get partial credits, right?
Yeah. Is the
If we can't answer a question, or it's more like a feature when it gets harder, can we like write out what we're thinking?
Yeah, sure.
the state or
Why New Jersey is a terrible state.
Are you in the math department?
Yes.
How do I go about getting a math minor?
Do you mean like the paperwork?
Yeah.
Yeah, it's, I'm not sure, actually. You should send in, the department chair is the one to talk to, and that is Professor Salin.
Okay.
You have him. If you send me an email, just so I don't forget it, and I'll get you in touch.
Right, thank you.
Sure. Hey.
It says like the set of A.
Yeah.
Can I do that, or I have to consider B because it says like all
Yeah,
cases should
right.
be A
This
and B.
this is better.
So this is better.
Yes.
Okay.
Although actually, A star also includes the empty string. This means all strings which use only a, but it could be nothing. And actually, this diagram does not accept the empty string.
Okay.
Because if
I
you do
have
the
to
empty string,
consider
it
that.
stops here. I think actually all you need to do is make this one accepting also.
Okay.
'Cause
So
then
just make this.
then the
accepting.
empty is also accepted. Yeah.
And so this is better because I should consider the case like in the set of A, B.
Yeah,
not
this
A,
is
B.
not right because you need also some arrow with B,
Okay.
and you don't have it. Yeah.
Okay. Thank you.
Yep. Hey,
I just had a few questions.
you're the one that sent me an
Yes.
email, right? Yeah, I don't know if there's another class in here. I think we
Oh.
should probably walk back to my office.
Okay,
Is that
that's
all right?
fine. Yeah.
I know that's a pain, it's in Benham.
No, definitely.
I don't know why they put